Okay, so in today's lecture, we're going to talk about um, dimension reduction. So dimension reduction is another important part in unsupervised learning. So just give you some motivation. One of the most important part is in current machine learning or data science, we are mostly likely to handle those high dimensional data. So these data could be images, could be videos, could be sound, could be document, could be biological data. Usually that has like high dimensional means we have a lot of features. For example, this amnesty data set has 784 pixels, but you can think about this as being 784 dimensions, but that just is really nothing compared to the phone that you have, which has and it could have 1 million pixels. So nowadays, in practical and situation, you actually encounter those like very high dimensional data from day to days. But this processing these kind of very high dimensional data could be very expensive just because of the curse of dimensionality. Think about the problem that we had even with amnesty data set. That's quite expensive already for the clustering, for the classification. Think about how much time you actually needed to process data in those Homo 1 to Homo 4. That's really, you can tell even with that simple data set. So it is, in practice, if we want to actually handle very high dimensional data sets, the first thing that we should do is we need to reduce the dimension of the data first before we actually and apply all sorts of clustering or dimension reduction or clustering or classification problems. So it's always the first thing that we should do in practice. But fortunately, so although those data and I'm in like and very high dimensions, but usually have there's some hidden low dimensional structures. What does that mean for the hidden low dimensional structure is these data point is roughly lies in the subspace of much lower dimensions. So that means you can think about we have the data set is living 784 dimensions, but actually these data could be embedded on subspaces maybe only that need 100 dimensions. So this is significant smaller compared to 784s. And we can even like push forward, like to say we only want to use it 2-dimension or 3-dimension to represent those images. So you can think about each image. I'm going to compress the dimension from 784 dimension into just 2-dimension, 3-dimension, and this image will be represented one dot in like 2 dimensions, like in a space of 3-dimensional spaces. So you can actually plot this dots and with 60,000 and amnesty images and become 60,000 like points on 2D or 3D and images. You can see how these and images allocated on these much lower dimensional spaces. So this will be really good for data visualization. And also it will be very efficient to use these kind of resources because compared to 784, which is higher dimensions, for 2 or 3 dimensions, we only need fractions of the memories, and that can speed up the process as well. And also, many images or the many data has a lot of like noisy part. And as once we like do this dimension reductions, it's also help us to like remove certain like noises. In fact, it can even improve the data quality as well. So and you can see in the lecture, we're going to show you even with the PCA or like all these kind of dimension reduction, so we reduce higher dimension into lower dimension somehow, and after that we can apply the classification problems. And it's possible this classification problems will give you even a better and accuracies compared to the original one. And also we can have a fast processing with this machine learning algorithms. Usually, for most of machine learning algorithms, they like to work with much lower dimension. and versus high dimensions. If we have a lower dimensions, then those like classification problems, regression problems, clustering problems will be processed faster. So this will be ideal in realistic situations. Okay, so let's just go back to the notepad. Then so this is just a very brief introduction on like why we need dimension reductions. Okay, so let's write down the goal here. The goal here is we want to learn a mapping. So I'm going to call this mapping, I'm going to call this phi, from high dimensional X in R big D into low dimensional Z R small d. So the key here, this X is high dimensional visible space. This low and Z is in low dimensional latent space. Okay. So for this course, we are going to just focus on one specific method. It's called PCA, Principal Component Analysis. So this is so the whole idea of the PCA is we're going to extract few but very informative combination of features in original data as our new data features. So the key is to extract few but very important informative combinations of informative of the key is linear combinations of the features. So this will be as my as the new data features. So let me just show one simple examples here. So think about the data is like that. Right, so I mean, if we look this data right here, so we know this has two features because it lives in two dimensions. So we have a feature one and a feature two. But we can think about a way that we can draw that we can define a subspace like this. So this is actually a V is a subspace. So and obviously this subspace has only it's one dimensional. And what you can do is you can project a point from one dimension and from two dimension into one dimension. So basically, I'm going to project my point on this 1D. So I'm doing like orthogonal projection here. such that I'm going to represent these points by those projection points on the subspace of V. So for example, if this point right here is called X of I, I'm going to call this, and the projected point is called X2 of I. Right, so this is, I'm going to using this X2 of I to represent this X of I. But why this is good enough? Because if we actually project this black dot into red dots, the error is small. So you can see right here, the error, because we use this kind of like orthogonal projections, such that to minimize the errors between these black points into the subspaces, if we are given the subspaces. So so we can actually represent and use the and the X of 2 of I is everything on the linear space of V, and we can use X2 of I from 1 to the n, which is in the subset of V, to represent the original data of I 1 to the n, which is in a subset of R big D. So if we can if we can use X2 of I, and in some senses this X2 of I so preserve the most important informations in for an X of I, then we can just directly apply either clustering algorithm or classification algorithm and for this X2 directly. So it's possible we can just work classifications directly. Instead of using the original data classification or clustering. All right. But obviously this has some benefit because the dimension of V is only one dimension. So we can use like one single digit to represent all these X2. Instead of using the 2-digit, so we can use only one dimension to represent all these X2. Instead of we have to using 2 dimensions to represent so an original and the data for the X right here. All right, so this is quite complicated, and let's just get into the math and I want to and explicitly formulate that so mathematically. So first thing that we need to do is we need to assume make some assumption here. So my assumption here is all my data is centered with a 0 mean. So if not, so we can subtract the mean of the data from each samples. Can subtract the mean of the from examples. So this is quite obvious right here because I mean if we have a I mean if we have a data matrix of X, so what you can do is you can take the bar of X, then what you do is you can this becomes a vector, and for each of X of I you can subtract X of bar, right? And it's such that as once we do this, we basically shifted the whole data set from some non-zero means into the origins, right? So this is the first thing that you need to do. If you want to apply the PCA here. But for simplicity, let's just assume this data is simply centered where the zero means. And my given data, so we don't have any label because we are working with unsupervised learning. We have a data that is X of I from 1 to the n. This is R big D. And also, we want to reduce this dimension and to small d. And we know this small d is significantly smaller than the big D. So the goal here is I want to find a d-dimensional representations that preserves the most informations in the data. So what does that mean? Mathematically speaking, as I said, we want to find out such kind of subspace of V with all these orthogonal in space, and in time, in some senses, we want our information loss to be as minimal as possible. So that means it has a two part. The first part is we need to find this d-dimensional representation. Because everything is being shifted to an origin, we can use the argument from the subspaces to work out. Then the second part is I want to emphasize this d-dimensional representation can preserve the most informations. Okay, so the first part to find this d-dimensional representation is I want to parameterize everything for this subspace V. So I'm gonna call this subspace in a d-dimensional subspace V. In R big D. So I'm going to parameterize that with orthonormal basis. So this orthonormal basis will be W1, W2 to WD. So the key of this is IE. For the orthonormal basis, that means WI and transpose WJ is equal to 0. So that means they're orthogonal. And WI, so this is for I is not equal to J. And for each of W of I, the 2 norm is equal to 1. So that means it has a unit length. So this is how we parameterize this d-dimensional subspaces. and which I call the V here. This is, and you can, and we want to project our and our points onto this subspaces here. Okay, so the second part is I want to preserve the most information. So what is the most information here? Right here, I mean, say we are giving this V right here. So what is the most information here? I want to orthogonal, and I want to project this onto this V right here. That if I want to using this x2 and the versus x, I want the distance between x2 and x to be as small as possible, right? So mathematically speaking, if you are given this V, which is I consider span of W1 to WD, so this is already given. I want to, so this is this I want to, and make sure my x2 is as close as x as possible. So that means I want my x minus summation of, since this x2 is on this, in the subspace of V, that means we can use the linear combination of this basis to represent x2. So this right here, you can think about this as being x2. All right, so this is, we take the square 2 norm, and we want to minimize the alpha 1 to alpha d, right? Such that this x2 can can approximate x as much as possible. That keeps the most information here. In particularly, this right here, this summation, this alpha j, wj, which here I call x2, is actually in the subspace of V. All right. This whole problem is, so now we have two problems. The first problem is we need to find the subspace. The second problem is, given the subspace, we need to solve this an optimization problem. But fortunately, this optimization problem is quite easy. So this is a simple quadratic optimization. And you probably have seen this before. The solution is immediate. In fact, the solution is this alpha j star to optimize this whole thing. It's nothing but inner product between x and wj. So then so you can think about and this can be solved by taking partial derivative with respect to alpha, then you just and assign everything to be 0. Then you can solve this as analytical solutions. So if we plug in this alpha j star into this, so that means my x2 is actually given by alpha j star of wj. This is equal to nothing but you plug in this value of x of wj and the wj, right? So this is actually the projection. So, and this actually has a name here. You probably have seen this in 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 optimization class. This is actually the projection of X. Onto the subspace V. In some senses, we can think about this is, so if this is my V right here, if this is my X right here, what we do is we are taking some orthogonal projections of X to the V. So this is the right angle. This point right here becomes my X2. So my X2 here is nothing but we project on each basis. That will be my weight to the basis. In some senses, this will be the nearest point because we do the orthogonal projection onto the V. That would be the nearest point in V to the point of X. So we can do all the point for xi onto this low dimensional and a subspace V. So that means these are amount of information that is being lost. It will lose some information. However, if all of my data of X is around V, like this situation right here, then this information loss is quite minimal because right here, right here, right here, right here, right here, these are all information loss. These are actually projection from xi to x2 of I. So this is not, this is not bad, but like the key is if we just happen to use this, getting this and a subspace of V, the information loss is quite minimized. So that means we hope all x of I, the whole data here are close to the subspace of V, right? But of course, that's my representation of my x2 here. But the big issue here, this x2 is still represented by big D dimensions. It's still, and still need D coordinate. So that means this is not fully like lower dimensions. Right, so what actually happened here is if we actually want to represent this x2 still using feature 1 and feature 2, that means we still need to use 2 coordinates to represent that x2 here, although this V is intrinsically one-dimensional. Right, so that's not really and what we want. We want is something that is intrinsically low dimensional. So we want X to be represented by only Z, which is in R small d. So what we do is we need to do some rotations here. So, and what is the means is we need to rotate this x2 to some like truly intrinsically d and small d dimension representations. So what we do right here, so we can rotate this v right here into a straight line here. Okay, sorry, let's just repeat. So the key is we want to rotate and this coordinate to get this like in small d dimension of data representation. So basically, this is my v right here. This is my subspace here. I'm going to rotate this, and we map this into this is my x of I tut, and this is x of I tut again, and so on. So these are all actually my v, but the actual value here that I'm going to use is say the actual value here to represent here will be just the weight. Since this is one dimension, so this we only have a w1, right? So this is actually my weight. In this case, it would just be my alpha 1 star. All right, so like in mathematics, what we do is we just rotate my and subspaces into to r small d, rotate v to r small d. Then then periods in my xi tut was actually represented in our big D because I'm using the big D dimension to represent the subspace of V. But after rotation, we can just simply use something called Z of I. Z of I and of I will be intrinsically being at a low dimension. So this is nothing but I'm taking this x of I, W1, and to x of I to WD. So this is actually, we only use it and use like a small d in the dimensions, right? So what we do is basically previously we might have in a W1 to W2, but we actually rotate it into the W1, W2 into the standard basis. Then we can get rid of this and the coordinate just using this like little d and a coordinate to represent my point. So here use z and z of I to represent x2 of I, right? So this is the very important part. So once we rotate that, then this like W1, W2 will coincide with x's. So and we can just using the coordinate. So in some sense, in other senses here, you can think about, and each coordinate here, this is corresponding to W1, and this is corresponding to WD. So if we want to map back, so you can just multiply this corresponding basis, it will like map back to this x2 of I, and nice and easy. So this is like, and not just one arrow, and it should be a double arrows. So, and you can get one and x2 of I to the z of I, or back from z of I to x2 of I. So the key here is we want to learn this z of I from 1 to the n, which is a subset of R small d, instead of we use the full data, or even x2 of I, because this is, although this is in subspaces, by still using big D dimensions or big D coordinate to represent that, because all of this is still a subset of R big D. All right. Okay, so the question is, how can we, and now, so now we basically solve the second question. So this is solved. If we are giving such kind of V, we can easily find out this R like alpha 1 into alpha D. But the question is, how can we solve the first one? How do we find out the V? Okay, so now the question is how, and go back to the first one, is how to find this low dimensional structure V. So the key here is we need to actually formulate everything mathematically, right? So, and the whole thing is, and the way to represent V is we using the span of W1 to WD. Okay. The key is we and with this V, we want our approximation error over the whole data set. And over the whole data set, which is X, is minimized. And what does that actually means? Is I have a data of X of I, and I have a data of X 2 of I, and I want to calculate the approximation error, which is basically the norm of these 2 points. I want to do it over the X. So this is summation from I from 1 to the n. I want this overall thing is minimized. With x2 of I is actually in the linear space of V. So here what we usually do is just sum of the square, like Euclidean distances. Okay, so, and the goal is we want to find, arguing the W1 to WD, right, such that this total approximation is minimized. But this is quite hard, right? So this is, I mean, a very tricky problems. So let's just think and things a little bit. So so let's take this and an objective function here. If we take this formula, subtract this. So this is sum of square distance. All right, so so we can think about this way. So we have a 2 point, right? So we have say this is the the x of I, and this is, I want to project this on the v, right? So that means I actually project this onto x of 2. So the error here is this one. So this is x minus of x2. Okay, so this is the error between x and x2. But we can take advantage of this whole thing is a right angle. So we can using like Pythagorean theorem. That means if we take this is a square plus x2 the square, this should be equal to x squared. Right? Because this square plus this square should be equal to this square. So this is a Pythagorean theorem. So that means what I got here is should be equal to norm of square of norm of x, subtract square of norm of x2. All right. So this is equal to sum of I to the n squared norm of x of I, subtract to so right here, I want to remind you my x of I, so x2 of I is actually summation of yi, wj, and the wj. Then this x of 2 of I, you can take take the inner product here, x of I. So this is sum of j. This is transpose of x of 2 of I. This, and this actually becomes let me think. Here, okay. Summation of I of x of I, wj, wj. So this transpose times itself, right? So here I'm using different index, using k here. So this is actually a double sum, but I want to emphasize and I want to remind you this wj transpose wk is equal to 0 if j is not equal to k. Wj and the wj transpose, this is equal to 1. Right, so this is definition coming from orthonormal. So that means most of the part it just cancels out. What actually left is when j equal to k, this is becomes summation j of x of I wj squared. Okay, so this is what actually left. So that means this is giving me summation of I from 1 to the n, summation j from 1 to the d of x of I of wj squared, right? And also we need to assume this wj j from 1 to d is orthonormal. Right, so this is basically the bottom line that we have. All right, so so we basically reformulate this problem into this subtract to this. But the key here is if we want to minimize this, right? So this is also minimize this of this whole thing. But I want to remind you this term is a constant because this is just basically my square, sum of square norms of my datas. All right. So that means to minimize this quantity, it's equivalent to maximize the second terms. So equivalently, minimizing my information loss, which is my approximation error here, it's equivalent with maximize summation I from 1 to the n, summation j from 1 to the d, x of I, wj squared. So this is actually has a name. So it's basically the variances of the projections. So why this is variance? Because I just square of this weight, but like we sum up the j from 1 to the d. So the reason that is called and the variance is because we have a zero mean. So that means the and so basically the expectation part it just becomes zero. So we don't worry about that. Okay. So then so this actually basically it will be equivalent that we want to maximize the variances of the projections. But of course, this is not enough. We want to make this to be and to has like and a vectorized formula and the vector and formulations here. So this is and we use double sum here. So and what we are going to do is we are going to switch the order. And we're going to switch the order of the summation here. So this becomes a maximum of 1 to the d. And I'm going to rewrite this as the following. This becomes wj transpose x transpose of x and the wj. So we are trying to maximize with respect to w1 to wd. Right? And also we need to assume all these w vector are orthonormal. This x is basically it's my data matrix we have x1 to x of n. So this is my data matrix, and each row contains the examples from x1 to xn. And also this x transpose of x here, and basically it's my summation of I from 1 to the n of my xi and xi transpose. And this is actually a D by D matrix. This is my covariance matrix of the data. So it has a name called covariance matrix. Of x. Of course, this has to what the zero means. So this is only to be the covariance of, matrix of data, only if because my x here has a zero mean. So we can just using x transpose x to be the covariance of the matrices. So that means for each component here, right here. So each component, so you can, I'm going to rewrite this to be a covariance matrix. Right, so this is actually the variances of the data along the direction of Wj. So we have a total and a covariance matrix. And what is this Wj transpose and the Wj is doing is we're only constrain our variances in the directions of like Wj's. And this is nothing but like the variance of data and along the direction of Wj. So you basically project all the data on the direction of Wj. That will be, and calculate variance. So this is basically the quantity, because if we actually calculate this mathematically, this is nothing but I from 1 to the n of my x of I, like inner product of my x of I and the Wj, then squared out. So this is basically the variances of the data and along the direction of Wj. Okay. All right, so I'm going to stop here. So this is, actually the formulations right here. In the next lecture, we are going to try to find a method to and to solve these optimization problems. And you can see this optimization problems is not easy. And we are optimized with respect to this W1 to WD. And we have like constraint subject to Wj here, j from 1 to d, are orthonormal basis. Right, so this is a very hard optimization problems. All right.